Hello everybody. In this video I would like to discuss with you a very interesting topic which is called a conduction heat transfer. But before we go through the topic in more details, we need to distinguish between two main definitions, which is the thermal energy and the heat. What is the difference between the thermal energy and the heat? Thermal energy is a form of an energy, such as work, such as chemical, internal energy, and so on. But the heat is the rate of transferring the thermal energy through a substance, okay? We can have any substance in one of the three phases as we know. We can have solid phase, liquid, gas phase. In case of the solid phase, the heat transfer it will be by conduction. In case in liquid or gas phases, it will be by convection. There is one more mechanism of heat transfer is known as radiation, and this radiation heat transfer we'll discuss it in the future in a separate video because it is involving in all of heat transfer other mechanisms. We will have it later on in details. But now we will go through the conduction heat transfer. Before we start to find out what is the equations regarding conduction heat transfer, I want to explain to you how is the molecules deformations in case of solid or liquid and gas. In case of solid, you will find each molecule has very small distance between it and the neighboring molecules, and they are connected together with very strong bond, which is need a very high energy, external energy, to break it in. This energy, when it breaks this bond, the material is going from solid phase to a liquid or gas phase. In a liquid or gases, this distance between two molecules it will be increased, and this strength or this bond strength it will be less than in a solid phase. Okay. The first scientist or one of the area scientists who studying the conduction heat transfer, he is Mr. Fourier, Joseph Fourier, and he is a French scientist, and he has conducted lots of experiments to find out how the conduction heat transfer works. And he find out that the conduction heat transfer rate is directly proportional to the exposed surface area times the temperature gradient through the substance or through the material thickness. Here there is a small diagram or very simple diagram explaining this equation. If we have a thickness solid material, let's say for example this solid material with a thickness delta A over X, okay, and this area has a thermal source here, like heat source exposed to a heat source. As a heat transfer, it will be from this surface area to the this surface area with a conduction heat transfer, and this will be in this direction, which means the temperature T1 is much higher than T2 because the heat transfer must be from the high to the low temperature. So the temperature gradient from this point it will be go down to this point. Okay, so the heat transfer rate, which is how much heat or how much thermal energy going through this material per second, is directly proportional to the surface area times the temperature gradient. The negative sign here is regarding to the temperature gradient, and I will show you how it works later. However, Mr. Fourier conducted lots of experiments to find the exact equation or the modeling, the numerical modeling to describe this phenomena, and he find out that he can put a constant here, which is called the material thermal conductivity. Material thermal conductivity is a changeable quantity from a material to other, and it can be considered one of the material properties. For instance, if I have a concrete, it will have a higher thermal conductivity comparing to a fiberglass or comparing to air and so on. Okay, the thermal conductivity has a unit watt per meter Kelvin, which is mean when I'm using this equation, the thickness of the material must be in meter. Okay, this equation is it has here the temperature gradient through the thickness or along the thickness of this material, but in real life we need an average, so we can calculate how much heat going through this substance per second. We can have the average heat transfer rate by integrating the previous equation with respect to the thickness and with respect to the temperature difference, as we mentioned before, that T1 must be higher than T2. Okay, so we can have here, after integrating this equation, we can have the final equation which describe the average heat transfer rate by conduction through a solid material, and this will be equal the thermal conductivity, which is lambda, times the surface area, exposed surface area, divided by x, which is the thickness, times the temperature difference from the high temperature to the low temperature. This equation we can use it, but when we are having this equation, we just assume that the heat transfer, it will be in one direction, which is from the high to the low temperature, not in two directions, which is mean it's in x, not in y. Okay, so all of the heat transfer, it will be in x only, x direction only. There is no y direction heat transfer, and we assume that it is a steady state, which is mean the temperature doesn't change with time. Perfect. We have here a small example which describing how is going on, or how we can use this equation. I have here 1 meter steel rod with a thermal conductivity 50 watt per meter Kelvin, with a cross-section area in here is 0.000625 meter square, and we have here this section area or cross-section area has 100 degrees Celsius, and the other section area at the end of the rod with 0 degrees Celsius. And here in this example, it says that this rod has been insulated along the rod, which means there is no heat transfer in that direction. That's very good. By all of this given informations, we can understand that the heat transfer will be in this direction, and it will be steady state case. Okay, to calculate the heat transfer rate, we can use the previous equation which we discussed before. So we have the temperature difference, which is 100 minus 0, and we have the cross-section area which has been given, we have the thermal conductivity, and we have the length of the rod, because the heat transfer, it will be in this direction, so this will be x, okay, which is 1 meter. Okay, this is very simple example to describe or to explain how we can use the previous equation. This diagram explaining what is the difference between the thermal conductivity for different materials. For instance, as we mentioned before that the concrete has very high thermal conductivity comparing to air, comparing to fiberglass, and so on. This is for your concern, just to know how the thermal conductivity changing with the material change. Okay. Here also there is a simple diagram to explaining that there is two things or two different conductivities, which is thermal conductivity and the electric conductivity. Thermal conductivity and electric conductivity is completely different, is not equal to each other, but we have both of them directly proportional to each other. For instance, if I have a temperature and a material we have with a high thermal conductivity, it should be with a high electric conductivity comparing to material with lower thermal conductivity. Okay, remember that the silver has very high thermal and electric conductivity. Okay, all of the previous discussion, it was regarding a homogeneous material, which is mean the material has been fabricated from the same raw material. If I have a wall, for instance, and this wall has been fabricated 100% concrete, we can call it as a homogeneous wall or homogeneous material. But if this wall has different layers from different raw materials, we can call it non-homogeneous material. So how we can calculate the heat transfer rate in case of non-homogeneous material? Here we go. If I have a wall, and this wall consisting of 3 different layers, and each layer has a different material with different thermal conductivity, okay, thermal conductivity changing with the material, and we have different thickness as well. Like the first layer has a thickness called XL, and the second one is XM, and the third or last one is XN. How we can calculate the heat transfer rate? I just know one only information, which is the heat transfer rate in this direction. It will be equal in each layer separately. For example, the heat transfer rate going through this first layer, it will be the same in this second layer, it will be the same in this third layer. Why? Because I assumed that there is no any heat rejected from this block or this element to the surrounding. Okay, it's well isolated system. Perfect. So this is what we have written here. Q, which is the heat transfer rate, is equal to the first layer heat transfer rate, which is XL times A divided by XL times temperature difference through the or along this first layer. Okay, this is first thing. The second thing, we can say that the temperature difference over the second layer will be T2 minus T3, and the heat transfer rate will be equal to this temperature difference times the surface area of the second layer divided by the thickness of second layer times the thermal conductivity of the second layer. The same thing will do it for the third layer. But in real life, it's impossible to calculate or to measure the temperature T2 and T3 because it is inside the wall. Okay, but we can measure T1 and T4. We can reach it, correct? So we want to have the flow rate, the heat transfer rate as a function of T1 and T4 only, because we can measure it. Okay, how we can do this? If I separate the temperature difference for each layer and put it in the left hand side terms like this, and we put all of other terms on the right hand side, so we can have 3 different equations or relations. T1 minus T2 is equal Q over A times XL divided by lambda L, which is the first layer thickness and first layer thermal conductivity. Here also T2 minus T3 equal Q over A times xm divided by lambda m, which is the second layer thermal conductivity and thickness, and the same thing for the third layer. If we adding these three equations together, we will find that we can have the heat transfer rate as a function of T1 minus T4. Okay, perfect. Remember that Q is equal the surface area times, here there is another parameter, or there is a value here, a big value, times the temperature difference. Okay, all of these equations driving, we consider that the surface area as the same surface area for all of different layers. If it is different from this layer to that layer, it will be a different scenario. Okay, another scenario to have another equation. However, this is the equation which we have. Okay, so this term, what we can do with it, to make it simple, we can call this term U value. Okay, and in lots of textbooks you will find they just mention it as a U value, like they can say to you as an engineer the U value of this material or the U value of this wall, it will be equal to a number. So the U value is equal to the thickness of each material or if each layer divided by its thermal conductivity, the sum of all of these materials together with a power minus 1. Okay, so it will be 1 divided by all of this term, this U value. Okay, perfect. I just want to mention something now, and then we can go through details in a few minutes, that there is something called R, which is the thermal resistance. This is equal to 1 over U. Remember this now, okay, for a moment. Okay, here we have 4 different materials. Each material has a different thickness, and each material has a different thermal conductivity. How we can calculate the U value of this? We can dividing each thickness divided by the thermal conductivity, sum all of together, and just give it with a power minus 1 as you see here in this equation. So we can have the U value, and if I have the inverse of this value, it will be the thermal resistance. Okay, why we said this thermal resistance definition? Sometimes to make it simple, we can just diagram or just have like analogy for the this mechanism, like an electric analogy. For instance, if I have very simple schematic diagram here to explain the idea, if I have 3 series material RL, RM, Rn, and I have a current here, and we have 2 points, point A and point B, and this point has a voltage difference which is V1 and V2. First of all, to calculate the resistance, the total resistance which is in series, we can sum all of this resistance and we can have R total. I here, okay, it will be the same like Q in our case in heat transfer, and delta V, it will be the same like delta T, which is driving force, correct? And the R, it will be 1 over U as we mentioned. If you remember, we have the main, or one of the main principles of the electric engineers, which is called the Ohm diagram, which is indicating that V, which is the voltage, equal I, which is the current, times R, which is the resistance. Correct? Perfect. If I put here delta V equal delta I times R, okay? So how we can write this in heat transfer, like as a modeling for heat transfer? Delta V, it will be delta V, it will be delta T equal Q times 1 over LU, which is mean Q equal U times delta T. Correct? Remember this. If you go in here, back in here, Q equal here we go, the main equation, Q equal area times delta T. Okay, this is for the unit thickness, and like this one, x over lambda, which is inside the U value, but here we don't have A in our case below, so this can be called heat flux, which is, for example, if I put it here, Q double bar equal Q, which we have it before, divided by A. Heat flux, the heat transfer rate per unit area. Okay? So we need just to remember what is the total heat transfer resistance and what is the U value, as I mentioned before, and we can calculate the heat transfer rate by remembering the electric one of the first principle, which is an Ohm law. So we can have the Q, which is the heat flux, equal U times delta T, and U, this one is 1 over U is equal to R, which is the heat transfer resistance. Okay? For instance, here, if I have different materials with different thickness and different thermal conductivity, as I mentioned before, that I can divide it, each thickness divided by the thermal conductivity, I have here like the resistance of it, okay, the resistance of each material, and if I have the sum of all of these value, I can have the total resistance. If I divided each value divided by the total resistance, I can have the percentage, how each material acts, or how much percentage of each material like playing roles in the total resistance. Okay, here, for example, in this table we can see that the isolation or insulation, it will be the highest resistance. That's why it's called insulation, to prevent any heat loss. I hope this video can give you a very simple knowledge about the conduction heat transfer theory, and if you need to ask me any questions, I'm very happy to receive your emails. My email on my page on YouTube, and you are welcome to write to me anytime. Thank you very much, and see you soon.